So in this video, I wanted to go over to the solutions to some of the practice problems that I've given on the Canvas website. The first set of questions here: suggest reagent that could be used for the following transformation. All right, first one is benzaldehyde to benzoic acid. All right, one bit of advice is that any time that you have a transformation where it's given to you as a name, definitely go ahead and write down the structure. All right, show the structure, and a lot of times that will be what gives it away. All right, so for example, this one right here, we're going from an aldehyde to a carboxylic acid. All right, and so whenever you're doing anything like alcohol, aldehyde, carboxylic acid, ketone, things that involve carbon-oxygen bonds, one thing that should come to mind is either oxidation or reduction. All right, and so for these types of reactions, I'm just going to call to your attention. Let me skip ahead here. This is a page of notes that we did a while back, where the way this is organized is that everything in this column right here was in the alcohol oxidation state. And depending on the type of alcohol, so the oxidations and reductions can go in different steps. All right. So notice that here, so everything's in the alcohol state. In this next column here, you've got everything, you've got a carbon double bond oxygen. All right, and it's different depending on whether it's from a primary alcohol or a secondary alcohol. But one last step would be one further step from this column, which would be this one right here, which would be the carboxylic acid oxidation state. All right, so notice here you're always going towards the right. All right, you're always going to a higher oxidation state. All right, so primary alcohol. So in these steps, the oxidation only happens with one reagent. All right, that's very much an oversimplification. But for what you're expected to know, the only oxidation agent that they talk about is acidified potassium dichromate, which you can abbreviate just by putting the dichromate ion /H+, which means it's going to be have some acid present. Okay, so notice that this would take a primary alcohol to an aldehyde, but it would also take an aldehyde to a carboxylic acid. All right, that would also take an alcohol to a ketone, and it would take this alcohol to a higher oxidation state, except for there is no higher oxidation state. So remember, whenever you're going higher in the oxidation, it's always going to involve the removal of a hydrogen from this carbon right here. So that's why you're able to get up to the carboxylic acid state if you start with a primary alcohol. But if you try oxidizing a secondary alcohol, you'll only be able to get to a ketone because there is no hydrogen on this carbon right here. All right. So the same going in the opposite direction. So if we're going to the left, we would be either removing an oxygen or adding hydrogens, and that's going to be a reduction. So if we're going to the left, there's two possible reagents. All right, lithium aluminum hydride or sodium borohydride, and these are the formulas for those. All right, so the only difference is that sodium borohydride is not quite as strong as lithium aluminum hydride. So if you're going to reduce a carboxylic acid to an alcohol, you would use lithium aluminum hydride. All right, but if you just needed to reduce either an aldehyde to an alcohol or a ketone to an alcohol, sodium borohydride would be fine. All right, so going back to the problem that we had, we're going from an aldehyde to a carboxylic acid. So that's an oxidation. So the appropriate reagent would be acidified potassium dichromate, which you can abbreviate like this. All right, going from an aldehyde to an alcohol. All right, and again, if you go back to that bit of notes that I gave you, an aldehyde to an alcohol, that would be able to be done with sodium borohydride. All right, that's a reduction. All right, going from this butene right here to 2-chlorobutane. All right, notice that this is an addition. All right, so one giveaway that this is an addition reaction is that you've gotten rid of the double bond. All right, so when you go from one chemical that's got a carbon-carbon double bond to one that doesn't, an addition reaction should be something that comes to mind. So take a look at what's been added. All right. Notice there's two hydrogens, one here and one here. And what the difference between these two is that you've added a chlorine to this atom and you've added an extra hydrogen to this atom right here. So that would be the addition of hydrogen chloride. All right. I want to point out that in this case, there's only one possible product that you can have if you treated this guy with HCl, because this is a symmetrical alkene. All right. If we added to this carbon first, you would get the exact same product if we had added to this carbon first. All right. And it's just like, and the reason is if you took this chlorine and you put it on this carbon, it would be the exact same chemical. All right. Last one, styrene to make ethylbenzene. All right. That's an addition reaction, but this is the that special type. It's a hydrogenation, where you're essentially adding a molecule of H2 to this. All right. So notice here there's one hydrogen and one hydrogen. Here you've got two hydrogens and two hydrogens. All right. So actually, sorry, that would be one hydrogen here and two hydrogens here, whereas here you've got two hydrogens and three hydrogens. So you've added a hydrogen atom to each of these two carbons. All right, so that requires the addition of H2. All right, and one quick way to remember it is that a hydrogenation is just simply getting rid of a double bond. All right, so both of them involve hydrogen as the reagent, and the only difference is the catalyst that you use. All right, you can either use hydrogen with palladium or hydrogen with nickel. All right. The next question talks about the difference between Markovnikov and non-Markovnikov addition to an alkene. And remember that this type of addition can only happen in non-symmetrical alkenes. All right. So if you take a look at this alkene right here, notice that if we split it down the middle, what you have on the left is different from what we have on the right. All right. So you're going to have that chance for either Markovnikov or non-Markovnikov addition. All right. So essentially, Markovnikov addition says that things are going to prefer to have the hydrogen added to the one that contains more hydrogens. All right. So this side right here has one hydrogen. This side right here only has none. And again, the reason for this preference of which one gets added to, which carbon adds to this reagent first, has to do with the stability of the intermediate. All right. So one way to think about this is we know that we're going to be that two of the electrons in this double bond are going to be attacking this hydrogen. All right. And the question is, are they going to add so that the electrons stay with this carbon, or are they going to add with the electrons staying with this carbon? All right. If they stay with this carbon right here, then they're going to be leaving this carbon right here, leaving a carbocation right here. If the electrons are going to be staying with this carbon when it adds, that's going to be leaving a carbocation here. And notice the way the arrow is drawn here. When the arrow is drawn slightly this way, think of it like a hinge, where it's like saying that there's a hinge right here and the door is going to open that way. All right, so the electrons stay connected here, and that's going to leave a carbocation right here. When I draw the arrow kind of going this way, that indicates that the door is kind of, think of the door as opening this way with the hinge right here, and that means that the door is not going to be connected to this carbon right here anymore. All right, so if we draw the results of that, all right, if the hydrogen gets added to this carbon right here, that puts the plus charge right here in the intermediate. Notice I should probably put a square brackets around that to indicate that it's an intermediate. All right. But if the hydrogen gets added to this carbon right here, that means that the carbocation is on this carbon. And the reason that that matters is that this is a tertiary carbocation, which is more stable. All right. So given the choice between these two, this would be the more stable of the carbocation intermediates, meaning that this is going to be the major product. All right, so this is your Markovnikov product. This is going to be your non-Markovnikov product. all right, which would be mean this would be the minor product that gets made. All right, and the next question asks for a pair of cis-trans isomers that involve a double bond. All right, so if you have a double bond and you have each of the carbons having one substituent which is not a hydrogen, you have that situation for cis-trans isomers. All right, so this would be an example of trans, and this would be cis right here. Again, cis is on the same side. All right, notice that there is also sometimes what are called cis-trans isomers when not with double bonds, but whenever you have a ring. All right, so you can use that. You can describe this type of an isomer right here as a cis isomer, because if you consider this cyclopentane ring to be in the plane of the paper, both of these chlorines would be on the same side of that ring. All right, and this right here would be examples of trans. All right, notice that these chlorines are across from each other. All right, notice one thing, there's actually two different isomers which are trans. These guys would actually be enantiomers of each other. But if you were to ask, if someone were to ask you to draw trans 1,2-dichlorocyclopentane, either of these right here would be fine. All right, so I just want to, just as a little reminder, when you have double bonds, you can either have cis-trans isomers, and you can also have the EZ isomers. And remember that the EZ isomer is when you have cis-trans is when you only have one substituent on each carbon, but if you have more than one substituent on each carbon, you would have to go to the EZ. So notice here that there's 1, 2, so there's 2 substituents on this carbon, and there's 1 on this right here. So this would be a situation where you would have to use the EZ way of identifying things. This would not be named as either a cis-trans isomer. All right, on the next one. All right, this is a mass spec problem. We have this compound right here, and it's got a significant peak at 57. All right, which would be the mass. All right, so what you always want to do with the mass spec problem is to go ahead and calculate what the mass is of your molecule. All right, so if we figure out the formula here, we can figure out the mass would be 74. Notice I'm doing something a little bit shorthand here. I'm just rounding these to whole numbers here, and with mass specs, that's something that you're going to see is that things are going to tend to be, first of all, you're most likely only going to be responsible, and I can tell you on my quizzes, only for things that are carbon, hydrogen, and oxygen. All right, so saying that the mass is 74 would be sufficient for what we're doing here. All right, but it says that you see a significant peak at 57. All right, so let's see what that means we lost. All right, so if we subtract these, what that means is there's a difference of 17. That means something with a mass of 17 mass units was lost from our molecule. All right, so if you look at this page in the data booklet, you'll take a look at the types of fragments that typically get lost from molecules. All right, and if you find something that you lost 17 units of mass, that would be an indication that you lost an OH somewhere. All right, so that would be diagnostic of losing an OH, and so what that means is that this part of the molecule right here got fragmented away, like this bond right here got broken. So there's a couple ways that you could answer it. One way would be to draw a formula like this. All right, that's just a shorthand formula of if we break that bond right there. Another would be just if we just count up all the atoms, you could say C4H9 with plus charge, or you could draw the molecule right here and just put a plus on the outside. All right, so I would find any of these right here to be acceptable. Similar type of problem. Cinnamaldehyde has got a mass spec. In the mass spec, we've got an ion at 103. So again, you're going to do the same thing. You're going to calculate what the molecular weight of this guy is. That's 132. But we've got this as an ion. All right, so let's see what we lost. We lost something which has got a mass of 29. All right, so for losing 29, it could be either of these two things right here. Either this or this. All right, so let's see the one that's most likely the case for our molecule. So it looks like this right here would be the most likely case. All right, that if that bond right there gets fragmented away, that's what we'd have. So these would be the two possible ions.